at Lehman. I don't see him. So I feel like people either teach on Monday, Wednesday, or Tuesday, Thursday, and I think we're on opposite days. So
Oh,
I
okay.
teach on Monday, Wednesday, and so I don't really see him. I haven't seen him very often, but yeah, he's definitely there. He's a good guy.
Yeah. Um, yeah, it's great to have you as our speaker today.
Yeah, good to be here. You can see the slides, right?
Yeah, yeah, yeah. I can see the slides. Also, sorry that my camera is kind of not working. So, yeah, also because of the internet connection, I kind of have to keep the camera off. So I apologize for that. Um, so I guess we're gonna start in 2 minutes. Just we should wait a little bit to for people to join. Also, I guess I saw Professor Rajali. If you are here, I also say hi to you. I can't see your ID, but I guess you joined the call.
Hello, Sajjad. I'm in the meeting, but I'm unknown here. Dear
It's
Sajjad?
great to have you here.
Okay.
Hi, Professor. It's great to have you here. I guess we should start. It's my pleasure to introduce Professor Brian Allen from Lehman College, City University of New York. He kindly accepted to give a talk at our seminar today, and his talk is about scalar curvature compactness conjecture in the conformal case. Thanks, Brian.
Yes, yeah. Thanks for the
Yeah,
invitation.
no worries. Yeah, yeah. Thank you.
Yeah, so this is what I'll be talking about, and yeah, thanks for everybody for coming. And so let me start by with some kind of big picture questions. So we're always going to be considering a Riemannian manifold. We'll almost always be considering a sequence of Riemannian manifolds and want to understand their convergence to a limit that might just be a metric space. But for now, let's just think about a Riemannian manifold. And we're going to be studying questions involving the scalar curvature. So this is the full trace of the Riemann tensor, or equivalently, the average of all section curvatures at a point. And we want to understand, what does the scalar curvature control and what does it not control is one way of thinking about it. And some big picture questions we can ask in this direction is like, what is a reasonable weak definition of scalar curvature? Which is analogous to the weak sectional or Ricci curvatures that we have on Alexandrov spaces or RCD spaces. We still don't have, we have some candidates for weak definitions, but there isn't a clear winner as far as which one is the correct one. So there's still a lot of work to be done there. And if you consider a sequence Riemannian manifolds with lower scalar curvature bounds, then in what sense do we expect the limit to converge, and what structure does limit space have? This is something that's been studied, of course, a lot with sectional curvature and Ricci curvature with Ricci limit spaces. So we want to ask similar questions with scalar curvature, sort of what are the right assumptions to have on the sequence and things like that. And so, you know, more generally, we can just ask the question, what is the scalar curvature control geometrically and analytically? So I won't necessarily answer any of these questions in the fullest sense today, but I will for sure give some answers to the last question, at least some indications. And of course, in geometric analysis, we're constantly curious about what analysis control can we get, and what does that say about the geometry. So to give you some idea of the kinds of things that have already been said in this area that you may or may not be familiar with, if we just take a Riemannian metric on an n-torus with non-negative scalar curvature, then we know that it has to be isometric to a flat torus. So there's no options there. This was proved by Shane and Yao and by Gromov and Lawson by different techniques. So Shane and Yao used minimal surface techniques, and Gromov and Lawson used spinner techniques. And so that's a rigidity statement. You know, scalar curvature is a very flexible definition. It's just the average of all sectional curvatures at a point, especially as the dimension gets higher. This is a very flexible definition, but this rigidity theorem tells us that it still can be rigid in certain cases, in particular on the topology of a torus. Something similar in general relativity in geometric analysis, we have that if you take an asymptotically flat manifold, this is a manifold that models a isolated gravitational system, and you know that it has non-negative and integrable scalar curvature, then we know it must have positive ADM mass. And so here the point is that the non-negativity of the scalar curvature is intimately tied to the positivity of the ADM mass. And there is also a rigidity statement for this, which says that if the ADM mass is 0, then the space has to be completely flat, just equal to a Euclidean space. So this was also proven by Shane and Yao using some minimal surface techniques, and Witten by using spinner techniques. And then one more rigidity statement that I just want to put in our minds in this talk is Leroux's theorem. So now we're on a n-sphere with scalar curvature larger than the round sphere. So that's n times n minus 1 in this case, and whose distance function is also bounded below by the round sphere's distance function. So any Riemannian metric that satisfies those two conditions on the scalar curvature and the distance function must actually be isometric to the unit round sphere. So this was proved by Leroux, and more recently it's been extended by these two teams to much weaker metrics. So not just smooth Riemannian metrics, they can prove it for I'm not going to remember the exact regularity, but basically for Sobolev metrics, they can also get this rigidity. So the point is that although scalar curvature is a very flexible quantity, it has rigidity in special cases that I've shown you just a few examples of. And these have been known for a while, as the dates on the slide are here. But in order to get a deeper understanding of this rigidity statements, we are going to ask corresponding stability statements. For each one of these, I'm going to give you a corresponding stability statement. So let's start with the then the way we can ask a stability question is if we take a sequence of Riemannian tori. So again, we have metrics that are on a torus, and let's say they have almost non-negative scalar curvature. So what do I mean by that is if you have a sequence indexed by j, and I want the scalar curvature to be bigger than or equal to some constant, some minus a constant over J, for instance, is an example. So in that sense that we could say it's almost non-negative along this sequence, then it should get close to the flat torus in some sense, but we have to be more precise about in what sense it converges to the flat torus. And I will show you pictures in a slide or two that will show you the things that we have to worry about in this kind of thing. Okay, but the point is that going from the rigidity statement to this stability statement should give us an even better understanding of what the scalar curvature can and cannot control, and it is getting us in the spirit of this sort of Ricci limit spaces, but now for scalar curvature type investigation. And there's been many special cases done by myself and many other people, but a most recent special case, which is somehow the most general case that's been done so far, has been done by Edward Bryden and Lizzie Chen recently. But still, the general case is still open, and this is a very difficult question. Then if we move to the second rigidity statement that I mentioned, this is when the scalar curvature is non-negative, then the ADM mass has to be positive, and the rigidity statement is that when the ADM mass is 0, the space has to be Euclidean space. So now we can ask, if we have a sequence of asymptotically flat Riemannian metrics that always have non-negative scalar curvature, and the ADM mass of the sequence is converging to 0, then in what sense are we close to Euclidean space? This question's been answered quite satisfactorily by Konghan Dong and Antoine Song recently. They give a technique for removing a bad set along the sequence. So you have a sequence of bad sets that you're going to remove, and they show that the away from the bad set, you get nice convergence to Euclidean space. So I will make some comments about this technique later on in the talk, because we're going to use a similar technique. But I will say that this question is still open in the sense that we still want to understand better what we can say about the bad set, what kind of phenomena can happen on the bad set. In any case, this is another stability question. And then the last stability question that I'll mention is related to the rigidity of Laroule's theorem. So now we say if we take a sequence of Riemannian n-spheres whose scalar curvature is almost larger than n times n minus 1. Again, when I say almost larger, I'm talking about a sequence indexed by j, and the scalar curvature is bigger than n times n minus 1 minus some sequence that's going to 0. And we require the distance functions to be bounded below by the unit sphere. Then in what sense is the sequence converging to the unit sphere? This one we have answered completely. So myself, Edward Bryden, and Dimitri gave an answer to this in dimension 3 using space-time harmonic functions. And then afterwards, Sven Hirsch and Yi Zhang gave an answer to this question in all dimensions using spinors. And they give many different answers, meaning many different notions of convergence. So I would say that they have answered this question quite satisfactorily. But the other two questions are still open in various different senses, depending on, well, the first question is very much open, and the second question, I think there's just more refinement that we can do to say more about the stability. Okay, so these stability questions, again, are a way of getting further information about what scalar curvature can and cannot control analytically and geometrically, and also give us an indication of what we should expect for like scalar curvature limit spaces, if you will. So now I want to try to give you a sense of what you have to worry about when you're trying to study problems like this. So here's a good picture. This comes from the paper of myself, Edward Bryden, and Dimitri Kligaris, where we're studying stability of Laroule's theorem. And basically for all these stability results involving scalar curvature, you always have to worry about these splines or these tentacles. And of course, in the picture, we're making it clear that there can be any number of these things appearing, and they can be quite complicated, having these kind of tree structures as you see here. And so in general, you should expect, if you're looking at a sequence satisfying some curvature bounds that you want to study, you should expect that you can have any number of these splines appearing, and then along the sequence you can have increasingly many of these splines. So right away we see that Gromov-Hausdorff convergence is not going to work, because if you remember Gromov's compactness theorem, in order for a Gromov-Hausdorff limit to exist, there must be a bound on the number of epsilon balls contained in your sequence, and you can always place an epsilon ball at the end of one of these splines, and if there's increasingly many of these splines, there will be increasingly many epsilon balls, and hence there cannot be a Gromov-Hausdorff limit. So when we try to study convergence in the scalar curvature regime, we know that Gromov-Hausdorff, the regular Gromov-Hausdorff convergence, is never going to be the right notion of convergence. And so there are several different notions of convergence that we can use instead, some of which will come up in this talk, but I just want to make it clear that Gromov-Hausdorff will not work on its own. Okay, so splines are a big phenomena that will happen in all these scalar curvature questions. Okay, another big phenomena that we need to be concerned about is what we call bubbling or other worlds appearing. So again, this came from our LaRuelle paper, so we have a background sphere, but I just want to make it very clear that it's really not, it's not really special to the LaRuelle theorem case. It's a universal phenomena that shows up in all these scalar curvature questions. And so what happens is that you get these little neck regions, which are sort of like a spline that you cut off the tip, and they're going to get increasingly thin along the neck here, but then behind them, you have really no control anymore. So you remember, you're thinking about stability of some rigidity theorem. So somehow in the white region, the rigidity theorem is stable in some sense that it's controlling the geometry pretty nicely, but then behind this neck, the rigidity, the almost rigidity, is not really working at all. And so that's why we try to draw this picture looking like a really funny shape behind here, which is just trying to indicate that we have very little control over what happens behind that neck. And so if you're trying to prove stability, the point is that you should not expect to be able to say anything about the orange region in a stable or rigid sense. So you have to deal with that in some way. So either, one way to try to deal with that is to cut out the orange region and say that it's like a bad region or a bad set and try to show stability away from the orange region. Or another possibility is to add some assumption that will not allow these kinds of neck regions to appear, which will then not allow these sort of orange regions to appear, and show stability with that additional assumption. But so we'll see some of those options appear later in the talk. But for now, I just want to mention that this is always a worry that we have to, always a phenomena that we have to consider. Okay, so and here I just show some not as good pictures actually, but other pictures where this can also happen on the torus, of course. So I have one spline on the torus, and you can imagine adding any number of these splines to a torus. And then on the right here, I also want to just point out that the bubbles can also be very nice and round and symmetric and things like that. They don't have to be bizarre. And again, these two phenomena are persistent in this business. Okay, but there's one more phenomena that we have to worry about that's sort of more recently come into the picture. And so this is what's been called drawstrings. Before I show you this phenomena related to scalar curvature, let me just show you the phenomena as like a metric geometry thing. Okay, so where we're not going to worry about curvature at all for a second. So now, if I don't worry about scalar curvature at all, or curvature in any sense, then I can just show you on a warp product. So that makes life simpler. Okay, so we're on a warp product like the one above. I'm just going to look at a two-dimensional warp product, but this is not special to two dimensions at all. It's just, I want to keep things as simple as possible. And so we have the following warping function, fj, where on an interval of length 2 over j, the function becomes quite small. And of course, the point is that it's 1 everywhere else. And as j goes to infinity, the function is 1 everywhere except for 0, right? We want to understand the geometry of such a thing. So on the right, we get this sort of distorted cylinder here. And the point is that although the Riemannian metric is not distorted many places except for at one circle along the center of this cylinder, the geometry is affected globally by such a thing, right? So these two red points are fairly far away, but they can take advantage of this shortcut that's appearing at the middle of the neck. And so that means the distance between these points is considerably shorter than they would be on a typical cylinder. And these examples, these simple examples were given by myself and Christina Sormani, where we were trying to just study the relationship between LP convergence of these warping functions and Gromov-Hausdorff and Sormani-Wenger intrinsic flat convergence. So I'll say a little bit about this theorem in a couple of slides. And we generalized this phenomena and what we observed to a general theorem, which I'll present. But it turns out that these shortcut examples can also be shown to exist if you have scalar curvature bounds in dimension n bigger than 4. This was shown by Lee, Neighbor, and Nomeyer in 2020. I just want to make it very clear that they cannot do it with warp products. It's a much more complicated construction that they need in order to get the scalar curvature bounds. But the metric geometry phenomena is the same in the limit, that you wind up like pulling, what we think about this as like pulling a path in the manifold to a point. And by pulling that path to a point, making all the distance along that path length 0, that has a global effect on the distance function between various different points by taking advantage of that shortcut. And then more recently, like we weren't sure if this could be done in dimension 3, but more recently, it's been shown by Dimitri Kazaris and Kai Xu that you can do this in dimension 3 as well. And I just want to mention that because it's in dimension 3, they have less to work with, less dimensions to work with. This construction is even more complicated, so it's definitely not a work product, but it has been shown to exist. So the takeaway from this slide is that these drawstrings, sort of shortcut examples where you just pull a path to a point inside of a sequence of Riemannian manifolds and get a metric space. This is also a persistent phenomena in all scalar curvature stability and in all these kinds of scalar curvature questions. Okay, so now that means there are 3 things we need to consider. That's splines, these bubbles in other worlds, and these drawstrings. Okay. So now I've given you a good idea of what geometric phenomena we need to worry about. And now I want to try to relate that to analysis. So in other words, like what kinds of analysis estimates should I expect in order to kind of control these geometric phenomena? So one way to try to study that is we're just going to look at a standard flat torus and look at metrics conformal to the standard flat torus. Okay, so that's what I'm going to look at in this part of the talk. And I'm not going to look at just general conformal metrics. I'm specifically going to blow up these conformal metrics at a point. So, and always these conformal metrics are going to be 1 outside of a ball of radius 2 over j. So outside of ball radius 2 over j, they're just going to be the regular old flat torus as far as the Riemannian structure is concerned. Inside a ball of radius 1 over j, they're going to blow up at some rate. And that's where we're going to play around with that rate of blow up. And on the annulus, it's just going to be an increasing function that interpolates in between. So we're not so worried about that interpolation region per se. That's just to make the function continuous and smooth, depending on what you want. But really what we're trying to do is study different blow-up rates, because those different blow-up rates are going to tell us sort of what estimates that we can get, or what estimates imply certain geometric phenomena. So that's what we're going to look at in the next slide. Okay, so here's a table that I want to walk us through. And on the top row, you'll see the most detail about the conformal blow-up, but I will say you can basically just ignore that top row if you want, because it's not, you don't necessarily need that level of detail to understand what I'm trying to give you here. Instead, perhaps I would suggest to focus on the second row, which is the LP convergence. So the point is, I'm going to look at 4 different example regimes here, and we're going to see that depending on which example regime you're in, you're going to get very different geometric phenomena, right? So in the first regime, in the first column, we're looking at the case where the example has LP convergence larger than the dimension. Okay, and it's also smaller than this other quantity, but what's really important here is that the LP convergence is strictly larger than the dimension of the manifold. Okay, so if you're in that case, then we know that the examples will always Gromov-Hausdorff converge to a flat torus. They will also always what's called Samani-Wenger intrinsic flat converge. I won't say much about this notion of convergence, but it's just to give you some very simple ideas about what it does. When it comes to splines, the intrinsic flat convergence sees the spline as just a part of the manifold whose volume is becoming very small, and so it will completely ignore these splines, and you'll converge. Like, for instance, you have a sphere with a bunch of splines coming off of it along a sequence, then that will converge to a regular sphere in this notion of convergence. So I won't say too much more about that, but still, this table will still be helpful. So in this first column, again, we have LP convergence larger than dimension, and the prototypical geometric phenomena then is that we get complete holder control on distances. So this is sort of too strong to expect for scalar curvature convergence, scalar curvature problems. Okay. This is more the kind of thing you expect for sectional curvature or possibly Ricci curvature kind of convergence. Okay, but still we need to understand where this cutoff is. Okay, so then in the second column, we are looking at examples where we blow up, but we have LP convergence of the conformal factor, for instance, for p less than or equal to the dimension. Whoops. So in this case, So in this case, we do not get Gromov-Hausdorff convergence to a flat torus, because this is the case where splines appear. Okay, so splines appear when you allow LP convergence for p less than or equal to the dimension. It's very important that we're allowing it to be equal to the dimension here. But again, the intrinsic flat convergence doesn't mind splines, so we do get convergence to a flat torus in that case. And again, I said this is where we expect splines. So since in all these scalar curvature stability questions, we're always going to expect splines, that means we should never expect to get an estimate consistent in the problem. And then in the next column, we allow LP convergence for p less than the dimension, strictly less than the dimension, but the LM is bounded now. So it's not converging in LM, but it's bounded in LM. This is when we get bubbling. So here, in both the Gromov-Hausdorff and the Swift sense, we do not get convergence to a flat torus if you think about blowing up the conformal factor at this rate, because bubbling is occurring. But this is useful to know that that's the level of analysis as far as LP bounds are concerned, where bubbling occurs. And if you only have convergence in the last column, strictly less than the dimension, so you only have LP convergence bounded away from the dimension, then you really lose geometric control. And now you can imagine what happening geometrically is, if you have like a flat torus, you can imagine like an infinite Scalar coming off of that's just touching the flat torus at a point. And so we've sort of lost all control of the geometry in that case. So what this table is telling us is that when we're looking for LP estimates, we are we should be thinking that we're going to be in the second and the third column, and we're going to want to impose some kinds of conditions that get us away from the third column and force us to be in the second column, depending on what our choices are for convergence. Okay, and it turns out that these examples, which myself and Christina Sermani studied in like 2018, 2019, every single one of these columns, or I shouldn't say every single one, but the first three have turned into papers where we show that this, what we studied here are just for examples, is actually indicating a general phenomena about convergence. So this first column, I've generalized and shown that if you have LP control for larger than dimension, then you get Holder control on distances, and you can think about this as like a Moiré inequality. And the other columns have been generalized as well. I won't say too much about that, but I think in the next slide, I will show you at least the one theorem that comes from all this investigation. So this is a theorem by myself, Raquel Perales, and Christina Sermani. We have a background compact, connected, oriented, smooth Riemannian manifold with boundaries. So that's also true at this point. But I'll just present the without boundary result. And you take a sequence of Riemannian metrics on this background manifold, which the sequence only needs to be continuous Riemannian metrics. And you know that the distances of the sequence is bounded below by 1 minus a sequence going to 0 times the background distance function. By the way, this condition in equation 3 is what we realized was necessary to disallow these shortcut examples or these drawstring examples I showed you earlier. So those examples that we studied motivated this hypothesis in the theorem. And you have a bound on diameter, so that's a very weak condition. And then you assume volume converges. So if you have these three conditions, then we can show that the sequence converges in this volume-preserving intrinsic flat sense, which I haven't defined, but you can think about this theorem as a sort of characterization of this kind of convergence, at least in this kind of special case for Riemannian metrics satisfying these bounds. And the point is that, basically in 5, we're roughly saying that all that can happen along the sequences is a bunch of splines can appear, right? And these splines can be really complicated and whatnot, but somehow that's all that can happen. And this notion of convergence is completely happy with splines. So the sequence will converge to the background Riemannian metric. And I mentioned this theorem because this is exactly the result that was used by myself, Ever Bryden, and Dimitri Kazaris to prove stability of the Laurel's theorem in dimension 3. And then this was also used by Sven Hirsch and Yi Zhang to prove stability of Laurel's theorem in all dimensions in the case of intrinsic flat convergence. And it came about because we studied all these different examples that I was showing you, blow up and this warp product shortcuts. Okay, but I'm actually not going to talk very much about, I'm not going to really use this theorem in this talk. I just wanted to mention it as an important tool in this area of scalar curvature. But the one drawback is that you need to be able to establish equation 3. And we show that the equation 3 is necessary, so it's not just a limitation of the theorem, it's really necessary for the conclusion. But oftentimes equation 3 is difficult to establish, in part because of the drawstring phenomena being a persistent issue in the scalar curvature problems. Okay, let me come to the question of this talk, though. So I've taken you on a journey through lots of different considerations, but all of these things were, everything we've talked about so far was to try to give you some idea of what we need to worry about in scalar curvature problems. And now I'm going to ask us a slightly more specific question. So given a sequence of compact Riemannian manifolds without boundary, if they have non-negative scalar curvature, the entire sequence, and the volume is bounded above and below. This and the diameter is bounded above. These two conditions are really just to make sure the sequence does not degenerate in an uninteresting way. So if you have these conditions, then the general question is, what do we need to add to this sequence, like any other further conditions we might need to add, so that the limit will be a rectifiable geodesic metric space with Euclidean tangent cones almost everywhere. So we want some kind of regularity on the limiting metric space, and we want the limiting metric space to have a weak positive scalar curvature. Okay. You can roughly think about this as like an analog to Ricci limit spaces, but it's much more vague because we don't quite know what the right way to formulate this is yet. But if we can formulate this correctly and get a notion of weak positive scalar curvature on the limit, then part of the hope is that this will be a good indication of what the correct notion of weak positive scalar curvature should be. Now, let me give you a slightly more specific version of this. So this is a version of the conjecture that was given by Cristina Sormani. I'm going to state it slightly differently, but it's mostly the same. And so we have a sequence now. Let's just think about three manifolds, because in some sense, if we can't understand the three manifold case, then we shouldn't hope to understand the larger manifold case. This is sort of the crucial dimension to start with. And again, we impose the same conditions on the scalar curvature, the volume, and the diameter. And as I mentioned before, we need some condition to rule out bubbling. And I'll show you a few examples of conditions we can use to rule out bubbling in the next slides, and some condition to rule out drawstrings. If you have those conditions, then again, there should exist a subsequence that converges in the volume-preserving intrinsic flat sense. So although I did not define this notion of convergence, I've mentioned a few times that it is resilient to splines, and I gave you a theorem which allows you to conclude this notion of convergence. So we want to show compactness, or one option is to show compactness with this notion of convergence. And then the limit space, we want to be a three-dimensional rectifiable geodesic metric space with Euclidean tangent cones almost everywhere. And we want the limit metric space to have a weak notion of positive scalar curvature. Okay, so this is the conjecture that we're going to address in the conformal case in this talk. Okay, but it turns out that, well, I should refine that a little bit. We're not going to be able to show this volume-preserving intrinsic flat convergence yet, but we're going to say something about this conjecture in the conformal case. And this has already been addressed by several groups before us in the rotationally symmetric case and in the warp product over spheres case. Okay. So let me just give you an example of how you can rule out bubbling. Like one example, or actually I'll give you two example assumptions that can rule out bubbling. And these are probably things you've seen in other parts of geometric analysis. So in particular, we can look at the Cheeger constant, where we just look at the area over the volume. Because it's the compact case, you have to look at the volume of sort of both regions that this surface splits the manifold into. But this is like a isoparametric constant, but you'll notice that there's no power in the denominator. It's not like the Euclidean isoparametric constant or anything like that. And so one of the reasons why we like this Cheeger constant assumption is because it allows for splines to persist. So this will not get rid of splines, but it will get rid of bubbling, because if you think about in this sort of peanut shaped picture that I showed you here, the area of this neck, if it was to become really small, but the volume of each of the bulbs was not becoming small, then the Cheeger constant will be becoming arbitrarily small, right? And so if we require the Cheeger constant to be bounded below by some positive constant lambda, and the area of the surface in the middle is going to zero, then that would have to force the volume of one of these bulbs to go to zero. So that's saying that if you did have bubbling, the bubble would have to become arbitrarily small in volume. And so they would kind of decrease, it would disappear in the limit as far as intrinsic flat convergence is concerned. So one option for ruling out bubbling that I particularly like is this Cheever constant. And from a geometric analysis point of view, part of the reason why I like this is because it has a nice geometric meaning that I've just kind of indicated to you, but it also is equivalent to Poincare inequality, so it has very obvious analytic utility as well. So it's very useful in that sense. But another example of a constant that you can impose on the sequence is to ask that the minimum area of all closed minimal surfaces in the manifold is bounded from below by some constant. Again, this also rules out bubbling because the neck in this sort of peanut picture would be a minimal surface. And if you ask that the area of that surface cannot go to zero, then you cannot have bubbles, right? And this one is well motivated by geometric analysis literature because minimal surfaces have played a major role in all these scalar curvature rigidity questions. So in any case, I'm just trying to give you some indication of the kinds of things that we impose in order to remove bubbling from a sequence in these scalar curvature stability questions. Okay, but let me be more concentrated at the end of this talk, or for the last 15, 20 minutes of this talk. Let me concentrate specifically on the conformal case and stop kind of being very general about this discussion. So if we're in the conformal case, and we're talking about now conformal to the round sphere specifically, and you have non-negative scalar curvature, so then that is 8, right? This equation in 8 is what the scalar curvature is for conformal metrics. And so if you rearrange that and integrate, then you get 9 right away. Okay, and so this is a good sanity check in the conformal case because it says that if you impose non-negative scalar curvature, then right away you get equation 9, which is not that strong, but it does give you compactness in the sense that, so for instance, if you impose, so 9 comes from non-negative scalar curvature, and then if you impose a volume bound like in 10 to make sure that the sequence doesn't degenerate in an uninteresting way, then 9 and 10 together will give you a W12 bound on the conformal factor, and that will imply at least weak convergence, right? So weak W12 convergence. So that's a very weak compactness, but it at least gives us a sanity check that there is some compactness if we impose these conditions, right? And then the goal of the research is to kind of bootstrap up and get much more than just this bare bones sort of weak compactness that we get right off the bat. Okay, and so one of the ways you might try to do that is 11 is the PDE inequality that's implied by non-negative scalar curvature, and so you may just try to squeeze out more regularity from equation 11, and that's what we did. Okay, so let me show you this this theorem. This is sort of the best that we can do so far in the scalar curvature compactness conjecture in the conformal case. So again, we're looking at a sequence of conformal metrics to the round sphere. We impose in 12 the usual conditions that you've been seeing, non-negative scalar curvature, and we impose a volume bound from above and below so that the sequence doesn't disappear to a point or blow up to infinity. And then in 13, this is a different condition that we're going to use in the conformal case to remove bubbling. And this condition appeared in a paper of myself in the conformal case of the rigidity of the torus. And it's a condition that's very useful in the conformal case. So I like it. And I'm interested in trying to get this condition in a general case, not just a conformal case. But for now, we'll just think about it in the conformal case. So what is it saying? If you measure the volume of a region U with respect to Gj, that will always be bigger than or equal to some constant lambda times the volume of that same set U with respect to the background round sphere raised to some power alpha. Okay, the way you should think about this, remember we already have an upper volume bound, so we're not really concerned about big sets U here. This condition is about, you want to think of small sets, small in the sense of volume. So what this is saying is that if a set is small with respect to volume, with respect to the background round sphere, then it has to be small with respect to the sequence. Okay, and so again, that's going to disallow bubbling, where you can imagine the sequence is concentrating more and more volume in a small region. That would create a bubble to appear, and this condition 13 is going to remove that possibility of bubbling. Okay, and you'll see later in the talk that this is very helpful from an analysis point of view. But for now, I just want to point out what it gets us geometrically. It removes bubbling. Okay, then there has to exist a subsequence that and a function that's in W1Q for these bounds here, so that we get strong LP convergence in the following range. And you should just note that what is this range telling you? So if you take the P and multiply by this exponent here, you'll see that the P is just M. So you're getting LP convergence for P less than the dimension. And so if you think back to the examples that I showed you before, this is exactly the range that we should expect. So that makes sense. It's not too strong is what I'm trying to say for the kind of scalar curvature questions we're talking about. And we get this weak convergence that comes for free, but we actually can get slightly better power here by milking some more regularity out of the PD inequality. And maybe slightly more interesting is we can show that the sequence actually has to be uniformly bounded from below the conformal factors, and the limiting function is bounded away from 0 and is lower semi-continuous. Okay, so this is sort of the most regularity that we were able to squeeze out of these functions so far. And it'd be nice if we can get more than that, but surprisingly, this is a very difficult question, and it's hard to get much more than this, but we can give a, so on the next slide, I'm going to give you maybe a more satisfying geometric notion of convergence here. But so far, all I've really mentioned is what I would consider analytic notions of convergence for the conformal factor. I just want to mention these lower bounds are really important geometrically because they tell you that the conformal factor cannot contain these sort of arbitrary shortcuts, right? So if the conformal factor in the limit is allowed to be 0, then you're saying that the distance function has these like shortcuts, and we are saying that that can't happen, at least. Right? So there's some geometric control coming from those last estimates. Well, let me just say that the sort of more geometric notion of convergence that we can find in this case, which is related to these recent papers by Konghan Dong and Antoine Song in the positive mass theorem case, is that we can, here in this theorem, we can look at Fj, so we're looking at the log of the conformal factor, and again, we can get these similar conditions that the log can't be arbitrarily small. There's some lower bound on it. It's lower semi-continuous. It converges in LP. These are all just analysis facts. But then on the bottom of the slide, we're saying that there is some measurable set, which we consider the bad set, so that the area of the boundary of this bad set plus the volume of this bad set has to go to 0. So that's in the sense that it's a bad set that we can ignore in the following sense. And if you look at the complement of that bad set, the volume of the complement is going to converge to the volume with respect to the limiting conformal factor. And then in 16, we can show that these logs of the conformal factor are becoming arbitrarily close in the C0 sense on the good set. Okay, so this is this gives you an idea of one of the options for convergence that's becoming quite popular in the scalar curvature stability and scalar curvature limit space sort of literature right now. which is this removing a bad set, showing that the bad set has small boundary area and small volume, and then showing that you get uniform convergence on the good part in the good set. And the point is that you just don't know what's happening on the bad set. There could be, you expect there to be lots of splines. Here we removed bubbles, so we don't expect bubbles, but there could also be shortcuts and drawstrings and things. Okay, but we'd like to strengthen this a little bit, because one drawback of this is we weren't able to show that the limiting conformal metric space has some notion of weak positive scalar curvature. So in the last couple of minutes here, I'm just going to adjust that a little bit. So let's think about, if we're in the case of a conformal Riemannian manifold, there's actually a very natural notion of weak scalar curvature. So, if you take a function u in this form who's in W12, we say if it weakly solves this inequality in 17 in the usual PDE sense of weak solving an inequality like this, then which is meaning you take test functions and you look at 18, and that's what it means to have weak non-negative scalar curvature. Right? So there's a very obvious definition of what weak positive scalar curvature should be in the conformal case, which also means that this is a nice testing ground to study this problem of compactness for scalar curvature, to try to see what we can do and then try to generalize it to arbitrary Riemannian metrics. Okay, so this is the weak notion of scalar curvature that we're going to use, just sort of weakly solve the PDE inequality. Okay, so this is going to be a very similar theorem to what I showed you earlier, but now I'm going to add one different assumption. So now the added assumption is that the total scalar curvature is going to be bounded from above, right? So the L1 integral of the scalar curvature along the sequence is bounded by some constant. The rest of the assumptions are the same as what I showed you before, but it turns out this total scalar curvature assumption is what is needed to get a little extra regularity that will give us the weakly positive scalar curvature in the limit. So now you don't have to pay too much attention to all this technical analysis if you don't want to, but we get slightly better spaces for the limit and slightly better weak convergence out of this. And the point is that this allows us to say a slightly stronger convergence, because now we're not talking about the log of the conformal factor, we're just talking about a certain power of the conformal factor. But again, we have this ZJ bad set where we remove it. It has small boundary area, has small volume, and off of the bad set on the complement, we're able to show this sort of uniform convergence of this particular power of the conformal factor. And it turns out that that is enough to get us weak non-negative scalar curvature of this limiting space. Okay, so that's the best that we can do in this conformal conformal setting so far. And in the last couple minutes, I'm just going to give you a very quick indication of how this is proved. But I do want to say that this part of the reason why I want to give you this indication is because this technique has been used now in many different papers. It was pioneered by Kong-Han Dong in the stability of the positive mass theorem case, but now it's such a good idea, it works really well in the scalar curvature setting, that it's been used now in many different scalar curvature problems to try to produce this good set, bad set type of convergence. So I just want to give you a slight indication of how this is done. So what we're going to do is just look at a good set where we say, just look at where the conformal factor is close to the limit. So E tau is just the set of all points where the conformal factor is close to the limit in some uniform sense. And of course, we need to argue that this set is becoming large in volume or something like that, right? So, but we can at least just define it. And so the idea of Kong-Han-Dong here was to take advantage of the co-area formula. So on the left, I'm just going to look at the area of the level sets of this thing. Because I'm looking at something that's not smooth, I have to look at like reduced boundaries and all that stuff. I'm going to hide all that technicalities, but I just want to mention that in the case that Kong-Han-Dong applied this and others have applied it, they know that the E tau is defined by a smooth function, so they don't have to worry about all that extra technicalities. But here, because the limiting conformal factor is not smooth, we have to be concerned about the extra technical issues here. But in any case, we can apply the co-area formula, and in 23, we get that this is what the co-area formula would tell us, and then we distribute the gradient and apply Holder's inequality, and we get 24. And the point is that in the first part of 24, that's an integral that we know is going to 0 by our L2 convergence estimates. And the second integral is something we know is bounded by our weak convergence estimates. And so we know 26, that this integral of the area of these level sets is small. Okay, and this technique this co-area formula idea is again been used many different times. So this is very useful in the scalar curvature regime. And so now I want to turn this into telling me that there's some level set that has small area. Okay, so we don't need to get too much into the details of all these choices we have to make, but basically you can make choices of a parameter tau in the allowable region, and the query argument I gave you in the last slide tells you that at least one of these level sets has to be smaller than C of j over epsilon j. If you choose tau appropriately, where which shows that there has to be some level set whose area. That's great, because then we just let Zj be the complement of that particular level set, and we already know that the area has to go to 0. Okay, so that's how you get the area to go to 0 of the bad set, but we also like to know that the volume of the bad set is going to 0, and then that will be some indication that we can ignore it in this convergence. So we can just continue this sort of idea here. And so now we use Chebyshev's inequality. So, I just want to look at the volume of the complement of the good set. So that's the bad set. And we look at the volume in 30. That means it's the super level set of this function. And Chebyshev's inequality just tells you that that's bounded by 1 over tau j squared times this integral. But this integral is something we know is going to 0 at the rate of this constant that depends on j. And again, we can choose tau or j so that this 31 gives us that the volume is going to 0. And of course, if the volume with respect to the background round sphere of the complement of this set is going to 0, then we know that the volume of the good set, E tau j, is converting to the volume of the sphere. But all this tells us is that if you measure the volume with respect to the background round sphere of the good set, it's going to converge to the round sphere. But the last thing we want to do is to show that the volume of the good set with respect to the sequence is converging to the volume of the sphere with respect to the limiting metric. So that's the last thing I'm just going to show you. And so here, I just want to indicate that the uniform integrability assumption that I showed you that gets rid of bubbling in the conformal case, from an analysis point of view, this is very important because it tells us that the ball in L1 is weakly compact, which normally, if you remember from functional analysis, the ball in L1 space is not weakly compact. But if you have this sort of uniform compactness, we compact in L1. And so that tells you that we can get volume convergence because if you look at the volume of the good set with respect to the sequence, that's just an integral of the conformal factor. And in 35, I can rewrite that as the integral over Sn minus the integral of the complement. And the integral of the sphere, so on the right side of 36, we know that that's going to be small. And so that forces the left-hand side of 36 to be small by the uniform integrability. And that forces 35 to converge to the full volume of the sphere with respect to the limit. Okay, so 37 is sort of the last nice estimate that we can get, showing that the volume of the good set with respect to the sequence is converging to the volume of the full sphere with respect to the limit. Okay, so that's the end of the talk. And yeah, thank you for your attention.
Thanks a lot, Brian. It was really awesome. Any questions for Brian? As people think about questions, I'm going to ask one. You also had this systolic condition, right? You said minimum of areas of minimal surfaces to be bounded away from zero. Do you get something in that direction? Do you need the n minus one dimensional, codimension one minimal submanifolds, or just surfaces, like minimal surfaces?
Yeah, this is.
And yeah.
Yeah, so far the minimal surface assumption has only been stated in the three-dimensional background manifold case. So then, yeah, you only need surfaces. We're not sure yet what you would need, but yeah, you might assume that you need like surfaces 2 dimensions through n minus 1 dimensions of bound or something. It gets a little ugly, but even in the three-dimensional case and assuming conformal, honestly, I just haven't been able to use the minimal min-A condition successfully. So I think it's an interesting area to try to, an interesting problem to try to work on. But it's the difficult part, in my opinion, is to get an analytic control from that assumption. So geometrically, it's clear what the control gives you, but it's difficult to get any analytic control out of it. That's why the assumptions that I tend to prefer are the Cheeger constant, because then I know I have a Poincare bound and I know how to use it analytically. And then the uniform integrability assumption, which we used in this case, again, gives clear analytic utility because it gives us that the L1, the ball in L1 in the function space is weakly compact. So I guess another way of saying the question is, what analytic control does the min-A condition give us? And we're not sure. But if someone can answer that question, then I think they would break through and possibly prove several results at once.
What about eigenvalue bounds? Like, is that might be stronger than isoperimetric, but like if you assume the some sort of eigenvalue lower bound or upper bound.
Yeah, I think this would also be interesting. I don't know of anyone I don't know that anyone's studied that yet. Of course, you just want to make sure you don't make it so strong that you get rid of like splines.
Right.
I think.
Yeah. Okay. Yeah, I really enjoyed your results. Yeah, great, good stuff. So, any questions for any more questions for Professor Brian Allen? Okay. So thank you a lot, Professor
Yeah.
Allen, Brian. Thanks for your time, and hopefully we can Yeah, and people say thank you. I enjoyed your talk. Thanks a lot again, and hopefully we can maybe talk in future about these kind of problems.
Yeah, that'd be great. Definitely. Yeah, thanks again. I
Yeah,
appreciate it.
yeah, thank you a lot. So if there is no more questions for Professor Allen, then yeah, people are applauding you. Um, okay, so if there is no more questions, then I guess yeah, we thank Professor Allen and thank you so much. And I guess this concludes the seminar. Thanks a lot,
Everyone.
Brian. Yeah, hopefully we can later on we can talk and see if we can take these kind of things further. Uh, yeah, thanks a lot. So thanks to everybody for attending the seminar, and I say goodbye to everybody. Thank you.